In this session, we'll be studying the equivalent circuit of DC motors and DC motors as well as of DC generators. As has already been informed that there are four types of DC machines. First one is a separately excited DC machine. In the case of a separately excited DC machine, the field circuit and the armature circuit are separate from each other. Uh, so, what this means is that the field windings can be represented separately, while the armature that hosts the uh, rotor as well can be represented separately. So this is the field circuit here of the separately excited DC motor, and this is the armature circuit. So there is the field windings will have their own resistance RF. Uh, Associated with the field winding will also be the inductance LF. We can also introduce an additional resistance that can be adjustable externally to this field circuit so that we can control the magnitude of current flowing in this field circuit. Now, irrespective of whether this is a DC motor or a DC machine, uh, the field windings will actually be energized by a field source, that will be a DC field, such that current IF will be established in this circuit. Now we know, since this current IF is a DC voltage, uh, owing to that nature, after steady state, this inductive component can be replaced simply by a short. So we can say the field equation is simply Vf is equal to If R adjacent plus Rf, current into resistance. Uh, as as soon as for the transient part, we can say there was LF DIF by dt. If we need to understand the transient stability of this DC machine, in that case, we'll also be taking into consideration the inductance of this field winding. But for the steady state analysis, LF, this part will be 0. Similarly, the armature, now this field circuit will remain same for a DC machine as DC motor as well as for a DC generator. There will be no change in the direction of current as shown. Now, in case the separately excited DC machine is behaving as a generator, that means we will be receiving voltage at this end. In that case, actually the field windings are inducing voltage EA across the armature. Uh, Now the armature will have their own resistance. The armature winding will have the resistance as shown here by the resistance Ra. Similarly, the armature winding will have some amount of inductance shown by inductance La. In that case, if it is now it's since it's behaving as a DC generator, the direction of current will be shown like this. Uh, that means in the field circuit, in the armature circuit for a DC generator, EA will be IA RA plus LA DIA by DT for if we are talking about transient stability analysis, LA DIA by DT plus the voltage VT. Since we are receiving the voltage VT as the output, so we'll write VT is equal to EA minus IA RA minus LA DIA by DT. For once the steady state is established in the DC machine, this part can be neglected, while the inductance LA will uh, offer a short will be shorted for a DC current IA. So our equation will simply reduce to VT is equal to EA minus IA RA. So this is the equation for a DC generator, a separately excited DC generator. Now if we take a case of a separately excited DC motor, in case of a separately excited DC motor, what we can note here is the armature circuit will now in case of a if it is behaving as a motor. Now we know in case of motor we are actually applying the voltage VT such that current in this circuit will be established in this direction IA. Now the voltage that is appears across the armature we know that is denoted by EB. That's actually the back EMF that's produced in case uh, we can use the same labels EA, but let's keep it EB for the time being. In the armature circuit now, VT will be equal to IA RA plus LA DIA by DT plus EB, that is the back EMF here. That means VT uh, is equal to IA RA plus EB. Once steady state is achieved, LADIA by dt will be equal to 0. So VT will be equal to IARA plus EB. VT is the applied voltage in case of a motor. IA will be the armature current. RA is the resistance of the armature windings. EB is the back EMF produced in the armature of the motor. In case it is behaving as a DC generator, we know that VT is equal to EA minus IARA, where EA will be the induced voltage in the armature because of the field circuit, because of the magnetic field produced by the field circuit, minus IARA. This is simply depending upon the direction of current. We are having the we know that in case of a DC generator, VT will be less as compared to EA, while as in case of a DC motor, VT will be greater as compared to EB. Uh, the losses the losses in the armature windings, that's IARA, the voltage drop taking place in the armature windings, in this case that's IARA, will have to be taken into account. So this is the equivalent circuit of a separately excited DC motor and its different equations. Secondly, we have a DC shunt motor. DC shunt machine. Now, in case of a DC shunt machine, the field windings and the armature windings are placed in parallel with each other. So we have this is the field circuit, this is the armature circuit. In parallel with it will be the field windings. So this will be the resistance of the field winding, this will be the inductance of the field winding, and this is the external resistance in the series with the field windings. Uh, so we have, this is the armature resistance. There we can also have the armature inductance. Now again, if it's a generator, VT will be the voltage output, whereas if it's a motor, VT will be the voltage input. So in case of a generator, know that since the direction of current will be IA will be flowing in this direction, the direction of current in the field circuit will remain same for uh, both modes, motoring mode as well as that to the of the IT is the voltage going to the terminals of this DC generator. So in this case, we can note that by using KVL and by actually using current divider laws, we can find out that IA in this case is equal to IF plus uh, IT, and uh, by voltage known voltage laws, we know that VT will also be equal to the voltage across this path, that is IF RF plus LF DIF by dt plus IF into R adjacent. Now I'll assume that we are only talking about steady state voltage equations. So IT will be simply uh, VT will be equal to IF into RF plus R adjacent, and VT will also be equal to uh, EA minus IARA. Uh, VT is equal to IF RF plus R adjacent, or as well as VT is equal to EA minus IARA. Now for the motoring mode, the only difference is we'll be showing the direction of current IA like this. IA will be in this direction now, as well as IT will be in this direction. So in the motoring mode, it will be IT that will be equal to IA plus IF, while as the equation for VT equal to RF plus R adjacent into IF will remain same. The equation VT is equal to EA plus IARA will now hold true. Now, instead of ET equal to EA minus IARA, we'll have ET equal to EA plus IARA, where EA will actually be the back EMF in case of the motoring mode. So this is about the shunt circuit. The third type of DC machine we have is the DC series motor, DC series DC machines, DC series machines. So in this case, the armature winding will be simply in series with the field windings. So this is the armature winding RA, LA. This is the field winding RF, LF, R adjacent. This is the voltage VT. This is the voltage EA at this very point. So for a generating operation, we can say the direction of IA will be like this. So we can say VT will be in that case EA minus IA RA plus RF plus R adjacent. Assuming that we have achieved steady state, LA and LF will behave as short. Normally, we do not even show these inductances in the equivalent circuit. We can simply show the resistances only in the equivalent circuit. So in a generating operation, EA will be VT plus this thing. So VT will be equal to EA minus IA, RA plus RF. And RA and RF in this case will be in the series. While as in case of a motoring mode, IA will be in this direction. So we can simply say at that time VT is equal to EA plus IA uh, into RA plus RF. Note that plus R adjacent. Note that EA will actually be the back EMF in case of a motoring mode. Uh, it's worth noting here that in case of a DC series motor, since the field windings are in series with the armature resistance, so we'll be using fewer turns of the field windings, while as in case of shunt winding, since so that RF actually offers lower resistance, whereas in case of a DC shunt motor, since the field winding is in parallel with the armature resistance, we can have uh, larger number of turns. So this is about DC series motor. The fourth type of motor that we have to study is the compound DC motor. Compound DC machine rather. Now, in case of a compound DC machine, we have the what we have is that we have effects of both. Mm, we have the field winding. We actually have two different types. We have the long shunt connection and the short shunt connection. Long shunt and short shunt. There are further two types of compound DC machine, the long shunt type and the short shunt type. In case of a long shunt type, what we have is that the field winding will be in shunt with the armature winding. Why? What we have in case of a compound DC machine is that the field windings will be in shunt as well as in series with the armature windings. There will be both configurations available. So this is the armature winding, RA. I'm not going to represent LA now here. There are two configurations. In the long shunt configuration, this is RF1, this is LF1, this will be RF2, this will be LF2. This is VT here, and this is EA. In the short shunt connection, this will be the armature resistance RA. This will be the field RF2, LF2. This will be RF1, LF1. So we have field windings, two parts of the field windings connected in series with the armature reaction winding as well as in shunt. Now whether the shunt appears directly with the armature, or first uh, if it directly appears, if it is immediately in parallel with the armature, it is known as the short shunt. If it is not immediately in parallel with the armature, well, the windings are first in series and then in shunt. It's known as a long shunt connection. Now, what happens here is that whether it's a generating mode or a motoring mode, uh, if VT is the applied voltage in a motoring mode, the current that will be flowing from here will be IT. Part of current will flow in this direction. That will be IP and IS. Where IP I'm writing here as the current flowing in the parallel path. IS is the current flowing in the series path. Again here, the current flowing here will be IT. The current flowing in this direction, let it be IF, IP rather, and the current flowing here will be IS. Uh, Also, we need to note here the um, windings, how we are winding LF1 and LF2. Uh, if they are wound in a fashion that the magnetomotive force produced by LF2 as well as the magnetomotive force produced by LF1, as shown here by the dot connection, will be additive in nature, it is known as cumulatively compound DC machine. The dot connection here simply represents that the current in both cases is flowing into the dot connection first. That means the magnetomotive force produced by both the windings will be positive. The summation of the magnetomotive force will add up. That's why it will be known as cumulatively compound. Now, this will be valid for both the cases, as well as if I am showing a dot connection here, dot connection here. So, this one will also be cumulatively compound. One thing is long shunt and short shunt, that actually denotes how the windings are connected with respect to the armature. If it is first shunt and then series, or it's first series then shunt. And in another case, we also need to note the way in which the manner in which the windings are wound. If that magnetomotive force produced by the field windings is heading up because of the shunt winding as well as of the series winding, it will be known as cumulatively compound. If the magnetomotive force, I am representing this square now here, that means in this case the current is first flowing into the square path, but it is in this case it is coming out of the square path. That means the magnetomotive force produced by one winding will be positive, while as the magnetomotive force produced by another winding will be uh, negative. The two magnetomotive forces will subtract each other, so it will be known as a differentially compound DC machine. Now, same is the case here. That is square is here and the square is here. This square actually represents the dot connection in case of the windings of the shunt field as well as of the series field. Accordingly, we can see that by using the Kirchhoff's law or the Kirchhoff voltage laws, we can find that Vt will be equal to uh, EA. In this case, Vt for a motoring mode, Vt will be equal to EA uh, plus IA RA plus I denoted actually IS here, so I'll be writing IS RA plus uh, IS RF1. This will be for the motoring mode. For the generating mode, it will simply be minus VT will be equal to EA minus ISRA minus ISRF1. For a short shunt machine, VT will simply be equal to, where this is EA, will be equal to EA plus ISRA for a motoring mode, and for a generating mode, it will be equal to VT equal to EA minus RSIA. sorry. Uh, Vt minus If Rf1 will be equal to Ea plus Isra. In case of a motor, in case of a generator, it will be since the direction of currents will now be like this, Vt plus If Rf1 will be equal to Ea minus Rs. It will be the voltage at this point that will be equal to voltage across this parallel path. So the voltage at this point will simply be equal to Vt minus the voltage drop across this resistance If Rf1. In case of a generator, it will be Rf1 plus into If plus Vt will be equal to Ea minus Isra. So this is about the four types of DC machines and their equivalent circuits and their uh, we have seen the equivalent circuits of the four types of circuits and their equations, their VT-EA relationships. Now, based upon these relationships, we have to actually solve for in generator we have to plot the VI characteristics and we have to plot the speed torque characteristics in case of a motor. For all the four cases, that we'll be studying in the next session.